Okay, thank you. So it's a pleasure to be back in Trento. I'm enjoying very much the discussions. It's clear that this works much better in real life than over Zoom. Sorry for the Zoom people. So everything I will say is of course done in various collaborations, mainly with our Madrid, Gothenburg, Aarhus group, but also sometimes with people from Leuven or Warsaw and other places. So I will talk, I picked 3 decays, Beryllium 11, to give you my sort of take on this drama that is happening there. And then some information about boron 8 measurements that we've done. And then my long-term affiliation with the carbon 12 through these 2 decays. I will give you the latest update of where I am with finishing that work. So let me start with this one here that you've seen a lot. Obviously, this is the beginning of the nuclear chart, the halo nuclei. So early on in the exploration of halo nuclei, it was realized that how those systems beta decay could be an interesting question. And it's often the first thing one can do is to see how do the system actually decay. So if you have a quite fragmented structure like a halo, it's an obvious thing to ask whether the halo and the core could have sort of separate decays, and how would that look in the data. So that was early on explored with the helium-6, for example, the deuteron branch, and also in lithium-11. So what these studies on beryllium-11, also boron-8, sort of fall in this kind of physics. So what happens when beryllium-11, a 1 neutron halo, decays, and similar with boron-8, which can be seen as a proton halo. So that's kind of the background for why we study these things. And then about 10 years ago, there was this paper here we published to put the focus on those 1 particle halos and their decay, beryllium-11 and boron-8. And in this paper, we published sort of the first numbers for branching ratios for beta-late proton emission, actually from both the decay of beryllium-11 and boron-8. So different things happening, either the halo neutron decaying in beryllium-11 or the core of boron-8 decaying in that decay. And at that time we found an upper limit, this one here, of 10⁻⁶ for the decay of beryllium-11, and also something like 2.6 × 10⁻⁵ for the decay of boron-8. But then let me just tell you a little bit about how this was done for the case of beryllium-11. So the idea here was that we did not want to look for the proton directly, because it was at that time thought to be almost impossible, but we learned that this is not possible later on. But the idea was to collect a lot of beryllium-11 in a catcher like this here, so this is the copper catcher, and then measure the gamma rays coming from the decay of this isotope, and then afterwards, after the experiment, take this sample here and put it to AMS analysis and just collect how many beryllium-10 isotopes were sitting there, and thereby by normalizing from this, find out what the branching ratio was. And this is in principle a good idea if you can find small enough amount of beryllium-10. And this beryllium-10 is a typical AMS isotopes used in many labs, so they know how to do that. Of course, there are some things that can go wrong. You can put the beryllium-11 in wrong places and not on the sample. So in order to check that, this is just why I show this figure here. So you have different detectors to find out that you have consistent count rates in these different detectors sitting at different places. And this consistency only exists if you actually have the main activity sitting in the right place. Okay, so then later on, in a new round of such a measurement, we found that this branching ratio was in fact not only a sort of an upper limit, but in fact a measurement. So there was excess amount of beryllium-10 found in this later measurement, leading to a branching ratio which was very surprising at the time, very high, close to 10⁻⁵. So so let me just, in this paper here, we analyzed how could this really happen? What could be the explanation? So let me just bring these plots out. This was shown by but not explained yesterday. So I just thought I would spend a little time to explain what this figure is trying to explain. So basically, the main ingredients are in this formula here. So it's kind of the branching ratio as function energy we're looking at in this formula. And there are Here the idea is you can only explain this kind of branching ratio if there's a resonance. And this formula tells you about the proton width of that resonance and where it is, and energy. And then there's just the beta phase factor here. And then the idea is let's put this proton width in the largest possible value, so the Wigner limit. And then what we don't know is what are the other decay possibilities of that resonance. So this is what is indicated by this gamma B here. So the total width is some other decay modes, and then the proton width. And this one is assumed to be maximal as a function of energy that will change, because we have this kind of expression here where this one has the maximum value. So we see here different plots corresponding to different estimations of what these other decay modes might be. And then we have this limit here that we measured. And basically there are two effects here. So if the resonance becomes close to the maximum energy, then the phase space becomes very small. And if the resonance comes close to the threshold, then this width becomes very small. So that's why you have this kind of bell curve distributions that are somehow has a value in the middle, and they go down either low energy or high energy. So you see that this branching ratio that we published allows you to say something about where that resonance would be and how other decay modes of that possible resonance could be in order to be consistent. And here in this formula, we put just the maximum of the gamma Taylor strengths of 3 to see what is actually possible. So this plot here is the kind of the background we are using to comment on how likely it could be that the branching ratio that was observed in Yazid's experiment are plausible or not. Over here is just the same thing. If you have as a function of where this resonance is, then given the branching ratio, that would correspond to different BGT values, obviously. So there's also a sort of a limit of where the resonance should be to be consistent with this kind of limits for what the BGT value can be. Okay, so then very surprisingly, there was this direct observation here where the position of the resonance was found, and also the branching ratio was now even larger than what we measured. So I will not dwell more time on that because that was discussed extensively yesterday. And then even more surprisingly, I would say, then there was this new measurement here also published in PRL, also discussed yesterday, where we learned that not only does the resonance actually exist where it was found in the decay, but it also has a appreciable alpha decay branching ratio, which means that the gamma Taylor strength is even larger if this is correct, right? Because then it's going up by a factor of 2 or 3. And this width here is now also, so that goes into the plot that I show you, that this makes the situation even more challenging to understand. And then to complicate the situation even more, we did a new measurement where we tried to reproduce this rather large branching ratio that we found in the first AMS measure, or the second one. And unfortunately, we then, when we looked at our samples, we measured several samples, we did not have a consistent outcome. So the different numbers written here for what the branch should be. Some of them are very large, and some of them are very small. So what we have to conclude is that there is some other source of beryllium 10 coming out of this iron source that somehow is contaminating our samples. That's the only way we can understand that. And this is not a consistent amount of background. It's somehow, we can understand it if this is something that comes out of the iron source mainly in the beginning of the experiment. Could be some water in the iron source in the beginning that is not pumped out properly. And then as a function of time, when this is pumped out, then this background disappears or is reduced significantly. So therefore, if we take some of the later samples, we can use this data to place an upper limit. That's sort of the best use of this data we could come up with. And then upper limit is of the order of 2 × 10⁻⁶. And just another relevant piece of information is that when we look at the decay of beryllium 11, obviously, there are other decay modes than this exotic beta-late photon emission that was also discussed to some extent already. And so here is the decay scheme, and that has been shown. So interesting that we are sitting up here close to the thresholds. My comment to Volja was that these log FT values are known for a number of transitions, and when you do a calculation, it would be nice to reproduce those other known transitions when you come up with a new one. It's a very large strength. So the point here is that when we then looked at the so this is an experiment done together with the Karoradis group in Leuven, where he used this implantation technique. This is the sort of the picture of the implantation inside this little strip detector, and then we just look for the subsequent decay events, where you measure the sum energy of the lithium and the alpha. Those are the branches we're interested in this experiment. So when you look at this spectrum, you get this kind of distribution here, and I'll try to explain you why it looks like that. So we do this kind of R matrix expansion here. So it's just what this basically means is that you can have a number of resonances, and you explain the width of those resonances in these kind of reduced widths here, and then you have feeding parameters for how much they are fed in the beta decay. And then there is the beta phase space factor and the barrier factor. And it looks a bit strange. So a good thing to do always is to factor out this phase space. Then what the intrinsic, this red curve really means is that you have a distribution like this. So there is a clear resonance here around 9.8, and then there's something going up here towards another resonance at around 11.5. So that's kind of why in this, to get this fit, we have to say that there are two resonances, one around 9.8 and another one 11.5. They interfere, so they have the same spin and parity. So the reason I take this along today as well is that if we look at this experiment, we had about 5 million implantations, and we had about 200,000 decay events, leading to a branching ratio of this size. So if you now take this branching ratio that was measured for this 1/2 plus state, and let's say this branching ratio in total should be about 2 to 3 × 10⁻⁵. If you take this value for granted, then you can estimate how many should we see in this experiment, and they should all be sitting out here. So just to show you how that would look, then we would expect about 140 decays from this state. So they should be sitting out here. So I just for fun, I wanted to illustrate. I found the data. So I just put, so where should this resonance be? It should be out here. So it's pretty clean actually. That's not much background. And then the area of that peak should be 140. So we can clearly exclude that from this data. That's just, I think, relevant piece of information. I didn't do credit to all. There's lots of papers on this, but they were discussed already, so I will not go into more detail about that. So that's the end of my take on beryllium 11. So let me move on to boron 8. So that was the other part of this paper 10 years ago. What can we say about boron 8? And if you look for boron 8, I think the theoretical estimates are that this beta flake proton branch could be of the order of 10⁻⁸. So obviously we want to reach that sensitivity. So in order to do that, you need to produce boron 8, obviously, with more statistics. So we've been trying to do that, and there was a PhD work by Silvia from Madrid that I just want to show a little bit the results here. So here the situation is, oops, I did that, but probably. So we have the decay scheme here. So what we are trying to do is to look for this region up here. So there, in this region, there is a doublet of 2+ states isospin mixed, and then there's a 1+ state up here that could emit photons. So what we're focusing on is to try to measure the speed decay to these very high lying states with better statistics than that was previously done. So here is the sort of the data from this experiment, and you see actually these two peaks here, and have to look at the you can't see it from this plot, but we due to the nice target group at Isolde, there was a new target made that could produce boron 8, so that we could make it something like 10⁵, 10⁶ per second. So actually the main problem was to have the right amount of intensity in the beam so that we could measure without distorting the spectrum in this highly populated region, and at the same time measure these high-lying transitions with the proper statistics. So again, in order to just understand this, what we are measuring, I just use the same kind of formula here. So let's divide by this phase space factor to see what it is we're actually measuring in terms of strength. So now we've done this transformation, you get this kind of plot here. So here we have a low lying 2+ resonance with first excited state and volumetric, and then we have that with in fact much higher strength, this doublet of 2+ states at high energy. And what I show here in this inset is what the data that we used in the to provide this limit of 10 to minus 5 10 years ago. So we barely saw the high line state in that experiment, but now we see it with very good. So we have this doublet now well measured, and we can then also, so where would the proton be in the spectrum? The proton would be down here. So that's that would be there should be a proton peak around 300 kV. So that's then the next issue. Let me just show you this first. But we also do this kind of fit here to understand what it is we've measured. So here's an arm matrix fit where we can fit this doublet and also the full spectrum, mainly coming from the 2+ first excited state, and then so that's not really the main focus of this talk today. Here is the if we look at the low energy part here, so this was the proton proton bounds should correspond to a peak like this, and we then try to put in by putting various amount of counts in such a peak to see what limit can we place. We do not see anything. The blue here is what we measure, so we can only put an upper limit, and that upper limit now is something like 5 10 to the minus 6, so an order of magnitude better than we had before. There's still a long way to go to reach this kind of estimate for what it should be 10 to the minus 8. So so there still remains something to do if one wants to look for that decay in boron 8. Okay, so that was the second part. So now the last part I will talk about is carbon 12. I hope you will indulge with that. It's still exotic, I would say, but it's not very far from the edge of stability. But nevertheless, we've had this system discussed a couple of times in this conference already. So we have Dean Lee, who showed this kind of distributions for how resonances could look inside, and maybe we could try to see whether we can get some data that would allow us to understand or test these kind of predictions. And he also showed this diagram here with the predictions for where there could be various resonances. And what was also shown in Ishikawa's talk yesterday was this result from ITEMBA, where they have measured 2 different reactions, carbon 12 alpha alpha prime, and also a PT reaction to look for a resonance, mainly so-called breathing mode of the Hoyle state. So I'll just show this just to illustrate you how complex and difficult this stuff is. So this is the plot that was also shown by Ishikawa, where it's talked about this ghost effect. So so you see, I mean, you have to put some doubt in whether this is how unique this kind of descriptions are. But what I will mainly be focusing on, what is happening here relatively close to the threshold, where in this kind of fit there is mainly 0+ and 2+ contribution. So just to illustrate what they were trying to do in this paper, so they were trying to look for this so-called breathing mode. So here's an indication of from that paper that this breathing mode is somehow distinguishable from other 0+ strength. So this is what they call 0+ delta, meaning that it's like a triangle of the Hoyle state that is sort of breathing or expanding as a collective mode. So this is so what we are trying to do is to instead of using this kind of reaction to use speech decay as a more selective approach, and I've showed this many times before, so I will not spend a lot of time on it. The idea simply is that if we can produce these rather exotic isotopes with short half-life, then we can use these selection rules to only populate 0+ and 2+ and 1+ resonances in the system, and therefore it might be easier to understand what is going on compared to when you do this type of reactions. And this plot here is just to show you that when you do that, you of course have different phase space modifications of this continuum when you populate it into different decays with different Q values, 13.3 and 17.3 MV. And we have used different techniques, and it's just a timeline so you can understand a little bit of how this is something I've been doing for almost 20 years or more than 20 years now. It's I'll promise you I'll soon be finished with it. So the idea is one can either do it in isol type things where you have a low energy beam that you stop in the foil and then measure the decay, or you can also do that with the Grishas method inside a TPC, or not only Grisha, but he did that for this decay. And then you can do it in inverse kinematics, and we did that together with the Carlo Arpe at KVI, whereby you implant the decays of the isotopes in the detector and measure the sum energy, which is a very nice constraint to have. So I just put on here, so this Texas active target thing entered the game here relatively recently. So why do we need to do this again? So as I showed you on this timeline, so we did these two measurements here. So why did we want to do them again? So my reason for saying that we were not quite done yet was that this decay mode here. So where you have decay to this continuum and decay via the excited state into the wave, not the ground state. This part here is well measured, I would say, but this part was not well measured, where you have decays that are sort of where the energy is equally shared. For that, you need to have detector setups that are relatively cover most of 4 pi, and that was not done in the previous experiments. We know how to analyze this type of events because we've studied this kind of Dalish distribution. That's why I show this plot here. For quite a number of states, we've studied that for this 1+ state here and also other states populated in reaction. So we know, we think, how to do that well. So I think it was a good opportunity to try to collect data or perhaps sufficient statistics of this decay mode as well, and to see whether that could then help clarify what's actually going on in this region. So that's the main reason why we did it again. So just to try to convince you that we know how to do this kind of thing, this is a paper we published this year, where we populated a 2- resonance in a reaction. We can do that at home with a small accelerator, protons on boron 11. So there's a strong resonance in this proton on boron 11 reaction that populates this 2- state. And there's actually been a recent discussion about what's happening in this decay. It goes back all the way to Rutherford, and then there was a measurement at the Duke University, I think about 7 years ago or so, where they published some data on that. So, but it had never been measured in complete kinematics, so we thought we should do that. So I just I will not go into much detail with this, but the idea with this kind of how we understand these Dalish distributions here is that there are 3 amplitudes that one has to add. These are complex amplitudes, and when one adds these amplitudes, they have this kind of complicated expression. Then there will be interference effects going on, and it's basically the fact that we have 3 bosons in the final state, and this leads to cancellation effects depending on what are the spin and parity of the state that is decaying. So for this particular 2- state, there is a hole in the middle which comes from this kind of cancellation. So for different states, different spins and parities, this kind of distribution will look differently because these cancellation effects are different. Sometimes it's also constructive interference. So that's so using this kind of expression, we should be able to get some sensitivity what's going on if we can measure these decays with sufficient statistics. That's the idea. So for the experimentalists, so we use this technique here. So in order to measure those rather rare decays, one has to have, as I said, a detector setup that has close to 4 pi coverage. Otherwise, you will not get this type of mode. So this is the one we use for nitrogen 12, and this is the one we use for boron 12. They can do that. So just to show you, here's a plot from the boron 12 experiment where we have this is when you measure 3 alpha particles in coincidence, and you ask what is the relative energy between 2 of those alpha particles. Then you get this kind of plot here. This peak here corresponds to the case to ground with away. Those are the ones we think we have already. but we have also now this okay amount of statistics for other types of decay. So for that part, at least we succeeded. So I will show you a couple of plots for how this looks, the data. And so you should have this kind of formula in mind. The same thing that I've been showing in previous slides. So we have so the decay rate is always given by some kind of matrix element, and then the phase space factor. And so therefore, if we take our measured branching ratio and divide it by the phase space factor, then we can get something which is related to the strength. So this is what I've done here. And then we have, in all the slides I will be showing, I compare those two mirror decays. The blue is boron 12 and the red is nitrogen 12. And then I've split it up into the decay modes here. So up here we have the decay mode going to the ground state of rate, and down here we have the decay mode not doing that. And you see we have these two distributions. And when we correct for this phase space, we get consistent distribution. So the fact that the blue one lies a little bit above, it means that there's probably a little bit of violation of the mirror symmetry. So there's more feeding, more strength in the decay of boron 12 than there is nitrogen 12. And then we see this strong peak at the 1+ state, which we see as a relatively narrow resonance. And above that, we only have data for the nitrogen 12 because there the Q value is higher. And then when you correct for this F, you see that the strength is actually also very high close to the threshold there. Just to so what's happening here, it's not easy to see when you have this kind of a range. So I just zoom in here so you can see what's actually happening when you zoom in for this. You see there's also good agreement between the two decays when you look at that region with a better zoom. A little bit strange, at least I don't understand. Then it seems to be that this mirror asymmetry that we see in this decay channel is not really present when we look at the other decay channel. So that's cannot really understand myself, but that seems to be what the data is telling us. So what can we do? So here's another check we can do. So let us take those two decay channels. So you have to, these two decay channels are separately corrected for detection efficiency, because that would be very different for decays going to the ground state or decays having this more uniform distributed geometry. So, but we correct those individually, then we add them, and then we can compare that to our measurement that we did at KVI, where we implanted the isotopes inside the detector, where we then, of course, get the sum of the decay modes. So this is what this rather busy plot is trying to illustrate. So if we, for example, look at the red and the green, you see that they agree. So the red is our new data for nitrogen 12, and the green is what we did at KVI in planning and detector. So we so this correction of different decay modes and adding leads to what we measured previously, and that also happens for the other decay boron 12. And we also see that this asymmetry, slightly higher beta feeding in the decay of boron 12, is confirmed when we compare the total data, not only at the individual channels. What else can we do? That's what I just showed, I think. So then the question is, what can we say about nuclear resonances? That's it's kind of why we want to measure this. Can we say something about? Can we say something about, for example, confirming Dean Lee's predictions for what there should be in this area? So let's start with the easy ones. So the 1+ states, well, you may not believe this one, but here's the isobaric analog state. It's kind of a peak here as the right place. And then there's the 1+ state here. So those ones are easy. They're also known before, so that's not really new. But the rest is not so easy. So how do we say something about what this means? And this was kind of what was discussed a little bit by Ishikawa yesterday. So one thing we know is that this ghost effect is present down here. So we know from previous measurements that in order to understand that there's this rather steep slope at high energy, and then there's a sort of enhancements at low energy, that comes from the interference between this ghost thing here, and a higher lying 0+ state. So that's kind of a robust thing we know already. But what else can we say? So I would like to do something that is robust in the sense that it does not depend on R matrix parameterization. So this is I showed this last year, but I've added a bit to it. So what the next thing we try to do is to let's just take those two decay modes and divide them with each other. So this is the excited state decay mode is really made divided by the sum that's plotted over here. So the basic idea is to say that okay, there's this kind of peak in the ground state distribution. And there's also this kind of peak that we've now measured in the excited state distribution. They don't quite seem to be at the same place. So let's see what the ratio looks like. So this is shown here. And then you have to think about what would you expect here. And if you have this mode here, the ground state mode, then you would expect there should be something here because this really made peak is also a peak that is close to a threshold, the same as the Hoyle state is. So that also must have this kind of ghost phenomena. It's a resonance very close to the threshold, so it must have a high energy tail as you go up higher up in the Coulomb area. So these curves here are how much would I predict from the measured contribution here that should be here as a function of energy, and that prediction depends on whether it's a 0+ or 2+ state that is present. So if it's a 2+ state, this prediction leads to a lower value and a higher value of the 0+ state. So you see up to about 3 MeV, the amount that we see here is actually more or less consistent what one would expect simply from this ghost effect. Yeah. Whereas when we reach 3 MeV, there seems to be an excess. There's more here. Which is not, if you would sort of make a prediction, you would say, okay, about 3 MeV, that's when the 2+ state starts to come in Brillouin. So this kind of makes sense. So we can say that probably this just means that it's the same state that is responsible for this, then has this expected amount here. But there's something else, there's a new decay mode coming in here because the 2+ state in Brillouin sort of comes in the window. So then can we then understand the amount? So this is what these curves here are trying to say. So let's say that the reduced width for this Brillouin 2+ branch has a certain size relative to the reduced width to the ground state. So these curves here is if that ratio, if the reduced width is twice and 5 times the reduced width to the ground state. So you see, it's kind of if you say it's 5 times, it overshoots here, but it explains the beginning here. So it's just to say you cannot explain this with one state only, with 2 different reduced widths to the 2 decay modes, because then this curve should go through all the data with the same kind of scaling factor. And we can say then, so there must be more than one state in this region. It's just a robust result, I would say. Okay, but we cannot really, at least not, I have not come up with other things one can say that is sort of robust. So then we have to go to this horrible R matrix stuff here, and I will not go into detail, but what we have done previously are 2 things. So we have done this kind of expression here, which basically allows you to do interference between different states in carbon-12. So let's say I have 2 0+ states in carbon-12. How do they interfere? Over here we have I've populated a given state in carbon-12, and I see how do these 3 alpha particles in the final state, how do they interfere and lead to this Dali spot. And we have previously not been able to do these things at the same time to make a common R matrix description of these 2 effects. So I'll just continue along this line, and then if I have 1 minute towards the end, I will tell you how we think it can be done together. So this is here, just looking at the Dali's distribution data. So this is from this non-ground state data, obviously. And let's see. Let me just show you here. Yeah, so these are nitrogen 12 and boron 12 data. So I forgot to explain. So what I did first here was to first show the full Dali plot, and then we use the 6-fold symmetry just to fold them into this little cake here, so that we sort of collect the statistics in a smaller region. So this is 4 and 12, and then we have nitrogen 12 here. Nitrogen 12, we have 2 more data, or 2 more Darley spots, because it has a higher Q value. This one here is the one we studied before, the 1 state, and that we understand. But you see there is quite very large variation in what is happening. So there's some hope that this will actually lead to some sensitivity. So when, sorry, I thought there was a plot here, but I somehow missed that. But then, okay, let me where that went. Maybe it's here. It is. So this is when we analyze those Darley plots, then you see that it comes out that it's mainly 0 plus. So this is data and fit of these Darley plots. So for each energy bin, we've made an analysis of what this Darley plot should look like, and then compared to the data, and we find 0 plus dominates in this region. Yeah. Let me just go here. So this, just to have a little bit of time. So this looks horrible, but it's just to show you. So we take this expression here. This is kind of the standard expression. Then we extend that to put it in this kind of transition matrix here, where we which has inside it this interference effect of different interfering particles in the final state. So this rather ugly expression, we've tried to do a simultaneous fit of all the data. So this is just my final slide, almost, where we have so we can fit at the same time all these Darley plots in different bins here, and then the ground state Guillemet distribution, and then we get this kind of for various types of assumptions for the number of states that are present. So here we have the Hoyle state, and then maybe there's a 0 plus and a 2 plus and 1 more 0 plus and another 2 plus, and we can fit it. I mean, it's possible to fit everything as long as we just put in enough states. But this is basically where I am sitting right now. So let me be honest, I don't know whether I trust this myself. Because I'm asking myself, what is the question? You know, what is the? So that's I think it's something I've said before. So is it meaningful that the experimentalists like me try to do this kind of exercise and come up with some values and then deliver that to some theoreticians who then try to reproduce those numbers, or should we somehow do this in another way? In this case, I think at least maybe another way of saying this is it could be nice with some theory support and how to actually explain these observables directly rather than going via this R matrix parameterization, which is perhaps not valid. So that is kind of maybe a point for discussion. So with that, I will just thank you for your attention.